Okay, let's start. It's almost on time. Thank you very much, Adam and Jared, for coming for this defense, to crossing the street that my students do quite often. I want to say a couple of words about Garrick. Garrick is my chemistry students. Most other students are coming from School of Engineering and Applied Sciences. And I just want to say not only that he is a phenomenal student, but also he keeps me in constant fear that yet another paper will hit my desk every 5 minutes. So he's using me and keeping me on my toes all the time, just to make sure that defense goes smoothly. I even put on my chemistry earrings that have different flasks. Chemistry flasks. And it has structural color in them that maybe you will mention a little bit. So without going further, I want to give the floor to Garrick to show his wonderful work that he has done within 5 years of his PhD.
4 years here.
And
No, 4. I arrived on Memorial Day, so it's less than 4. It's 3 years and 11 months now.
okay, even more so.
We're not done. We're not done. We have right. But good afternoon, and thank you everyone for coming in person on Zoom. I'm Garrick, chemistry PhD candidate with Professor Joanna Heisenberg at Harvard. Today, I will share our raspberry colloid templating strategy, and I'll illustrate how this strategy can serve as a model thermocatalytic platform. I'm aiming to present for about 45 minutes uninterrupted, then I can answer some of your questions afterwards. Every time I try this, but we'll see if it works. Before I start, let me first introduce my research interests and training before and during my PhD. My research training is centered around colloidal materials. They are design, synthesis, characterization, and testing for a variety of energy applications in harvesting, conversion, and storage. As an undergrad at the National University of Singapore, I synthesized near-infrared emitting core shell quantum dots for applications in LEDs, sunlight harvesting, and bioimaging. I then spent a year in a national lab in Singapore synthesizing 2D material heterostructures based on an emerging class of 2D materials called MXenes for electrocatalysis. More recently, the past 4 years, I have been completing my PhD in Joanna Heisenberg's lab at Harvard, working on catalyst designs that leverage on colloidal, sol-gel, and nanocrystal chemistry, together with nanoscale interfacial phenomena effects, which I will discuss in this talk. In my work, I developed heterogeneous catalytic materials, which are indispensable to the production of over 90% of the chemicals and starting materials used today. These catalysts typically comprise of catalytically active nanoparticles stabilized on solid supports. Industrially, such catalysts are conveniently prepared through impregnation procedures, whereby metallic precursor solutions are added to a support material. A drying and high-temperature calcination step nucleates the nanoparticles, but often leads to a broad heterogeneity in nanoparticle sizes and compositions, especially when multiple metallic precursors are used. To make matters worse, under high temperatures and pressures during catalytic evaluation, these nanoparticles often agglomerate and sinter to form larger nanoparticles, resulting in catalyst deactivation. Since multiple structural parameters are coupled together and change during synthesis and reaction, these existing catalyst preparative methods are therefore not best suited to elucidate clear structure property relationships to guide and inform our future catalyst design. To address this challenge, we developed a raspberry colloid templating catalyst platform, or RCT in short, inspired by the structure of the morpho butterfly wings. In this RCT method, pre-synthesized colloidal nanoparticles are attached to templating colloids to form nanoparticle decorated raspberry colloids. These raspberry colloids are then self-assembled and filled with metal oxide precursors. A templating colloid removal step forms the support and yields the final RCT catalyst. The RCT method here seeks to address the two major limitations of the impregnation method. One, the RCT method uses pre-synthesized colloidal nanoparticles, which decouples the nanoparticle and the support formation steps from each other for independent variation of either component. You will notice that I do not label the chemical identity of the nanoparticles, templating colloids, or support precursor to highlight and illustrate the chemical flexibility of this RCT platform. Two, because of how the support precursor wets and forms around the nanoparticles, practically all the nanoparticles are partially embedded within the support, which confers enhanced thermocatalytic stability against nanoparticle sintering while maintaining high accessibility to our reactants. In my PhD, my vision for this RCT platform is driven by one question. How can I employ this modular RCT strategy as a model thermocatalytic platform to deconvolute the individual effects of traditionally coupled structural descriptors and derive clear structure property relationships to guide our future catalyst design? In this talk, I will share how I approach this question. I will illustrate how nanoparticle properties, either individually at the individual nanoparticle level or collectively as a nanoparticle ensemble effect, can be independently tuned to alter catalytic outcomes. I will then discuss how the RCT method, because of its high degree of nanoparticle embedding in the support, is strategically positioned to study and exploit nanoparticle support interfaces in both synthesis and catalysis. The structural properties that I choose to investigate in my PhD, such as nanoparticle size, nanoparticle proximity, and nanoparticle support interfaces, are found in practically all nanoparticle supported catalysts, regardless of their preparation method. Therefore, I anticipate that the effects of these individual structural properties, which I have deconvoluted and studied in my PhD, will be broadly translatable to existing catalyst preparative methods to design more active, selective, and stable catalysts in the future. In the interest of time, I will briefly summarize this first section in the next slide. Then I will focus on publication number 2 in the first half of my talk and publication 8 in the second half of my talk. Let me very briefly discuss individual properties. The modular RCT method distinctly decouples the nanoparticle and the support formation steps for independent variation at different length scales. At the nanoscale, we can isolate and tune the properties of the support and that of the individual nanoparticles, such as the support chemistry, nanoparticle composition, and the nanoparticle size. At the mesoscale, we can control the spatial position and localization of nanoparticles within each pore, which I will elaborate from the next slide onwards. At the larger macroscopic scale, the template size dictates the RCT catalyst pore size and its connectivity to control mass transport properties. Finally, the RCT catalyst can be fabricated on a variety of preformed catalyst support surfaces as films or bricks, or take on discrete standalone shapes like microspheres and freestanding flakes. Beyond the individual nanoparticle properties, the RCT method allows us to control properties of the nanoparticles as a collective entity, such as the interparticle distance and the nanoparticle localization. In this first half of my talk, I will illustrate how nanoparticle proximity as a collective ensemble property can be used as a mesoscale tool to direct our reaction selectivity. When we consider thermocatalysis, the effects of nanoparticle proximity is primarily centered around stability, with shorter interparticle distances resulting in nanoparticle aggregation and growth. Beyond its impact on stability, we could not find sufficient literature on the direct impact of nanoparticle proximity on other thermocatalytic performance indicators, such as activity or selectivity, without being confounded by accompanying changes to the nanoparticle size distribution. A systematic investigation on the effects of nanoparticle proximity on thermocatalysis is challenging using traditional impregnation methods, where the metal precursor is introduced to the support, then nanoparticle nucleation is induced. This is because a higher metal precursor concentration nucleates more nanoparticles, thereby reducing the nanoparticle proximity from D1 to D2, but concurrently yields larger nanoparticles and thus does not decouple the isolated effects of nanoparticle proximity or the nanoparticle size on catalysis. Deconvoluting nanoparticle proximity effects from changes in nanoparticle size thus require a different catalyst platform capable of independently varying both these potential descriptors. The RCT method allows us to fabricate a series of catalysts, and in this case, comprising palladium gold nanoparticles supported on silica, whose average interparticle distance was tuned by metal loading. As the ratio of the nanoparticles to templating colloid increases, the metal loading can be reliably increased from 5 to 20%, thereby reducing the interparticle distance at a fixed nanoparticle size. Additionally, the partial embedment of practically all the nanoparticles confer strong resistance against nanoparticle sintering during catalytic evaluation. We use this platform to investigate the isolated effects of interparticle distance on the liquid phase hydrogenation of benzaldehyde to benzyl alcohol and toluene, which was chosen as our model reaction because its catalytic mechanism and kinetic parameters are already well established. Now, to further decouple the metal loading from the interparticle distance, the highly modular RCT method allows for the mixing of nanoparticle decorated raspberry colloids with nanoparticle-free templating colloids in a pre-calculated ratio. For example, by mixing raspberry colloids that would result in a 20% catalyst with nanoparticle-free templating colloids in a 1:3 ratio, we obtain a final 5% catalyst, but with an interparticle distance that resembles the 20% catalyst instead. This way, we can compare catalysts at the same 5% metal loading, but with different interparticle distances. As expected, we found that a higher metal loading resulted in a higher nanoparticle density and thus shorter average interparticle distances. You can see this in both the raspberry colloids we used and the RCT catalysts we produced. To quantify the average interparticle distance of our three-dimensional catalysts, we used electron tomography to determine the three-dimensional spatial positions for each nanoparticle for over 2,000 nanoparticles. We then wrote a script to find the shortest interparticle distance for each nanoparticle within each pore. On average, the interparticle distance decreases from 21 nanometers to 12 nanometers as the metal loading was increased from 5 to 20%, in line with either a geometric model or a statistical prediction. Importantly, this interparticle distance was tuned at a preserved nanoparticle size distribution, which indicated that we successfully decoupled nanoparticle proximity from nanoparticle size. This deconvolution cannot be achieved using existing catalyst preparative methods. Beyond the fixed nanoparticle size, we also had to ensure that all the catalysts were physically and chemically identical to each other, with the only exception being the controlled metal loading and thus the average interparticle distance. We saw that the metal loading increased linearly with the volume of nanoparticle solution added, evident from the ICP elemental analysis and the increasing XPS peak heights of both palladium and gold. Moreover, the nanoparticle composition and oxidation states were also preserved, as seen from the ICP elemental composition data and the unchanged XPS peak positions for the metals. This conclusion was substantiated by the linear relationship between the metal loading and the quantity of CO chemisorb, indicating that the palladium site accessibility scales linearly and was unrestricted in the investigated range of metal loadings. We are thus confident that across the entire RCT catalyst platform, no physical or chemical differences were detected apart from the interparticle distances. This condition facilitates a systematic investigation into the isolated effects of nanoparticle proximity on catalytic performance. We first investigated the nanoparticle proximity effect using a constant metal mass by adjusting the catalyst mass to consider the metal loading. The benzaldehyde conversion rates, as shown in the curves here, were similar regardless of interparticle distance. Interestingly, the selectivity towards benzyl alcohol was dependent on interparticle distances, as catalysts with a shorter interparticle distance show a lower selectivity to benzyl alcohol than catalysts with larger interparticle distances. Next, we tested catalysts using a fixed amount of catalyst mass. Unsurprisingly, the 20 weight percent catalyst in maroon over here showed a high activity due to its higher metal mass. But the effect of interparticle distance on nanoparticle proximity, on catalytic selectivity, was now even more pronounced. Finally, we maintain both aforementioned conditions simultaneously by comparing the locally high metal density catalyst against a regular 5 weight percent catalyst. As I've mentioned earlier, the catalyst over here has the same 5 weight percent metal loading as a regular 5 weight percent catalyst, but has an interparticle distance that resembles the 20 weight percent catalyst instead. We found that the benzaldehyde catalytic activity was similar in both 5 weight percent catalysts, regardless of interparticle distance. However, catalysts prepared using raspberry colloids with a higher nanoparticle density and thus shorter average interparticle distances still displayed a lower selectivity to benzyl alcohol. Taken all together, our catalytic results illustrate that the interparticle distance independently controls selectivity without compromising activity and stability. We then performed some kinetic analysis and elucidated that toluene was produced in 2 phases. Toluene production during the active benzaldehyde conversion phase in the gray region here was very high and cannot be solely explained by the conversion of free benzyl alcohol into liquid. Our kinetic analysis also revealed to us that the direct benzaldehyde to toluene conversion was much slower than that of benzyl alcohol to toluene. Hence, we modeled toluene to be produced primarily from benzyl alcohol with a rate R2 that depended on factors both internal to and external to the active site. To determine any intrinsic changes to our catalysts, we performed ex situ characterization of our used catalysts and found no differences in the nanoparticle size distribution, composition, oxidation states, kinetic rate orders, and the apparent activation energy. It was thus unlikely to us that the nature of its active site and the absorption coefficient has changed substantially after the reaction. For the external factors, we tested the catalyst at a constant active site concentration using a fixed metal mass and under constant bulk mass transport characteristics using a fixed catalyst mass. In fact, you saw in the previous slide that we tested both these conditions independently and simultaneously, and the selectivity differences still persisted. Ruling out these reasons led us to deduce that differences in the local benzyl alcohol concentration amongst the catalysts caused by the different interparticle distances as the most plausible explanation for the selectivity differences. We thus investigated how the interparticle distance affects the local benzyl alcohol concentration to explain the high, rapid, and proximity-dependent toluene production during benzaldehyde conversion. Since the nanoparticles actively produce benzyl alcohol during benzaldehyde conversion, we hypothesized that nanoparticle proximity plays a pivotal role in augmenting the benzyl alcohol concentration profile locally around the nanoparticles. This would consequently affect transient benzyl alcohol diffusion and reabsorption onto the nanoparticles for toluene formation. Similar phenomena were proposed in electrocatalysis, but it's not fully clarified in thermocatalysis, possibly due to the high propensity for nanoparticle sintering in conventionally prepared catalysts under typical thermocatalytic reaction conditions. To evaluate how the nanoparticle proximity affects the local benzyl alcohol concentration profile and subsequently the selectivity, we used the interparticle distance data and simulated the local benzyl alcohol concentration profile around the nanoparticles. In this model, nanoparticles act as point sources to produce benzyl alcohol, which diffuses into the bulk liquid. The benzyl alcohol concentration is visualized using a color scale bar, with red indicating a higher concentration and blue indicating a lower concentration. The trend of the local benzyl alcohol concentration as a function of interparticle distance is summarized here. As the 5% catalysts show a local benzyl alcohol concentration about half that of the 20% catalyst, which you can see by comparing this point to this point, the likelihood of benzyl alcohol reabsorption on the 5% catalyst is greatly reduced, thereby minimizing toluene production and increasing benzyl alcohol yield. This conclusion agrees with our experimental data, which indicate a substantial enhancement in the selectivity towards benzyl alcohol from 54 to 99% as the average interparticle distance increases from 12 to 21 nanometers. The benzyl alcohol selectivity trend at different interparticle distances also depict a negative relationship to the local benzyl alcohol concentration trend, underscoring the strong correlation between nanoparticle proximity and product selectivity. Here, we argue that the as-produced benzyl alcohol adsorbed on the nanoparticle can either 1. Dissolve into the bulk as free benzyl alcohol, or stay within the nanoparticle's vicinity. For the latter scenario, benzyl alcohol can dissolve from the nanoparticle and be readily reabsorbed by an adjacent nanoparticle or back to the same nanoparticle without diffusing into the bulk in both cases. Paths 2 and 3 depend on yield toluene, and depend on the interparticle distance, as a higher local benzyl alcohol concentration would increase effective benzyl alcohol reabsorption to form toluene. Alternatively, benzyl alcohol can remain adsorbed on the same nanoparticle and form toluene. Since the lifetime of benzyl alcohol adsorbed in the nanoparticle depends on the benzyl alcohol surface coverage on the active sites of the nanoparticle, we propose that paths 1 and 3b likewise depend on the interparticle distance. Thus, we put forward that the interparticle distance affects toluene production and hence selectivity through 2 competing routes. A larger interparticle distance favors path 1, which results in freely diffusing benzyl alcohol in the bulk. On the other hand, a shorter interparticle distance favors path 2 and path 3, where benzyl alcohol is reabsorbed to form toluene. Now we can combine our findings all together. Catalysts with a shorter interparticle distance exhibit an enhanced local benzyl alcohol concentration profile between the nanoparticles. Thus, a greater fraction of the as-produced benzyl alcohol is readily reabsorbed to an adjacent nanoparticle or back to the same nanoparticle instead of diffusing into the bulk as free benzyl alcohol. This results in more undesired toluene produced and a poorer selectivity towards the desirable benzyl alcohol intermediate. Overall, this work illustrates that the same catalyst under the same reaction conditions can lead to different catalytic outcomes by simply manipulating the nanoparticle placements. After learning that nanoparticle proximity controls selectivity, the next natural question to ask is, what about the effects of nanoparticle size? Since the RCT platform uses pre-synthesized colloidal nanoparticles, we can easily change the nanoparticle size while maintaining a preset ratio of nanoparticles to templating colloids to keep the interparticle distance fixed at 21 or 12 nanometers. I will not have time to elaborate on this work, but our key takeaway is that nanoparticle size controls activity, while nanoparticle proximity controls selectivity separately and independently from each other. Therefore, we maximize the desirable benzyl alcohol yield using catalysts with smaller nanoparticles separated by larger interparticle distances to overcome trade-offs between activity and selectivity. This brings me to the end of the first half of my talk. I have illustrated how the RCT platform provides high synthetic modularity and chemical flexibility to the use of pre-synthesized colloidal nanoparticles. Together with the partial nanoparticle embedding feature, these nanoparticles are stabilized during catalysis to study individual nanoparticle properties without accompanying changes to other descriptors of interest. The colloidal templating design of the RCT platform also confers synthetic flexibility in the nanoparticle spatial localization and their placements, which allowed us to study transport and potentially field effects arising from collective nanoparticle ensembles. Beyond its modular tunability, another unique feature of the RCT method is that it derives catalysts with nanoparticles partially embedded within the support, which not only improves catalytic stability against sintering, but also increases the nanoparticle support interfacial length, which is demarcated by this box. This is in contrast to conventionally prepared catalysts, where nanoparticles are formed or attached onto the surfaces of support materials. In this second half of my talk, I will share how the RCT platform can be employed to disentangle support and embedding effects, and illustrate how nanoparticle embedding can be used as a synthetic tool to accentuate the catalytic roles of this nanoparticle support interface. Metal support interfaces are found in practically all nanoparticle-supported catalysts, and their interactions are relevant for a wide range of catalytic reactions. These interactions are typically tuned by changing the properties of the nanoparticles or by changing the properties of the support. However, the common impregnation method to prepare these catalysts are not best suited to investigate metal support interactions for three reasons. First, the support chemistry strongly influences the nanoparticle nucleation characteristics, which often results in different nanoparticle properties when nucleated on different supports. This strong interdependence of support and nanoparticle properties precludes independent variation to isolate effects arising solely from nanoparticle support interactions. Second, nucleating nanoparticles directly on the support surfaces limits our synthetic ability to tune the already limited nanoparticle support interfacial parameter. Third, under thermocatalytic conditions of high temperature, pressure, and mechanical agitation, these impregnated catalysts are prone to nanoparticle leaching and sintering, which further confounds our catalytic analysis. To address these limitations, we, together with other researchers, have identified partial nanoparticle embedding into the support as a key design feature to increase the nanoparticle support interfacial length and improve catalyst stability against sintering. Some synthetic strategies adopted by other groups to achieve this embedding feature include metal oxide migration by strong metal support interactions, or metal oxide overgrowth through dry or wet chemical means. One common challenge in these strategies is to devise synthetic ways to control the nanoparticle embedding levels while preventing complete nanoparticle encapsulation. Here, we use the RCT Catalyst platform, as practically all the nanoparticles are partially embedded within the support. Moreover, the modular RCT approach affords independent variation of support properties without changing the nanoparticle properties, which cannot be achieved using existing catalyst preparative methods. To disentangle the support and embedding effects from each other, we first prepared RCT catalysts comprising palladium-13 gold-87 nanoparticles, partially embedded in either a silica or a titania support. The gold-rich nanoparticle composition allows us to compare the gold-silica interface, which is inactive for a probe reaction, against the gold-titania interface, which we hypothesize may be active for this same reaction. The dilute palladium content in the nanoparticles accelerates hydrogen activation or hydrogenation. As a control to investigate the effects of partial nanoparticle embedding on catalytic performance, we also prepared the non-embedded catalysts by immobilizing the same palladium gold nanoparticles onto morphologically identical silica or titanium support surfaces. For a fair comparison between the catalysts, we had to first ensure that the catalysts were similar apart from the support chemistry. Indeed, we observed no differences between the RCT catalysts in terms of its macroscopic structure, nanoparticle size distribution, nanoparticle elemental composition and distribution. Partial nanoparticle embedding in the RCT catalyst was visualized, then quantified by electron tomography. On average, about 85% of the nanoparticle surface was embedded into the support, leaving about 15% of the nanoparticle surface area exposed to the reactants. These largely compatible physical and chemical properties between the catalysts thus facilitated a fair comparison of their catalytic performances. The non-embedded and partially embedded RCT catalysts were tested using benzaldehyde hydrogenation as our probe reaction, building on our earlier work. All the catalysts were very selective to benzyl alcohol and stable after reaction, which allowed us to compare differences in the intrinsic catalytic activities alone. We first compared the non-embedded catalysts to determine the effects of support chemistry. The silica-supported catalyst was moderately active due to palladium ensembles on the nanoparticle surface that activated hydrogen and bind to benzaldehyde. A slightly higher activity in the titanium-supported catalyst suggests additional benzaldehyde binding at this nanoparticle titanium support interface. Next, we compare the non-embedded to the partially embedded RCT catalyst to study the effects of nanoparticle embedding. Partial nanoparticle embedding enhances the activity of the titanium-supported catalyst by 4.1 folds, which was initially surprising to us, since the RCT catalyst exposed only about 15% of the nanoparticle surface area to reactants. This activity enhancement due to partial nanoparticle embedding, together with a stronger support effect in the RCT catalyst, is highly associated with an increase in the nanoparticle support interfacial parameter, and thus the number of gold titanium interfacial sites. Additionally, to ensure that the catalytic trends were not specific to just one nanoparticle composition, we also prepared catalysts with a range of other palladium gold nanoparticle compositions and verified that the support effect applied similarly to all other bimetallic palladium gold nanoparticle compositions we prepared, but not to the monometallic gold or the monometallic palladium catalysts. Importantly, the similar activities of the palladium catalyst confirms that the enhanced activity of the titanium-supported RCT catalysts are due to the gold titanium interfacial sites and not due to the palladium titanium interfacial sites or the titanium surface sites. To elucidate the underlying mechanism behind the support and embedding effects, we performed benzaldehyde temperature programmed desorption in combination with DFT calculations to investigate how benzaldehyde binds to the surface sites. I will not go into the details, but state our main finding that benzaldehyde binds to the palladium ensembles and the gold titanium interfacial sites. As benzaldehyde binds to both the gold titanium interfacial sites and the palladium ensembles, we quantified the ratio of these binding sites to estimate their relative contributions to their catalytic activity. In the titanium-supported RCT catalyst, the number of gold titanium interfacial sites was 4.2 times higher than that of the palladium ensemble sites. Strikingly, this site counting result parallels our activity results earlier. Thus, we attribute the strong 2.6-fold activity enhancement primarily due to the high abundance of gold titanium interfacial sites, which was created by partial nanoparticle embedding to facilitate additional benzaldehyde binding in the titanium-supported catalysts. We can now summarize the roles of the different active sites for benzaldehyde binding and hydrogen activation, the two key elementary steps in catalytic benzaldehyde hydrogenation. In the non-embedded silica catalyst, its modest activity was derived from palladium ensembles on the nanoparticle surface that activated hydrogen and bind to benzaldehyde. When the support was changed to titanium, the activity was enhanced slightly due to additional benzaldehyde binding at the gold-titanium interface on top of benzaldehyde already bound to the surface palladium ensembles on the nanoparticles. Since the gold-titanium interfacial sites activated hydrogen poorly from our experimental results, we deduced that the benzaldehyde bound at this interface was hydrogenated by hydrogen spillover from palladium ensembles on the nanoparticle surface that activated hydrogen. Importantly, partial nanoparticle embedding into the titanium support enhances activity by a further 4.1 folds as the nanoparticle support interfacial parameter, and thus the number of gold titanium interfacial sites was increased, which enhanced benzaldehyde adsorption capacity and reaction at the interface. Before I summarize this second half of my work, I want to highlight that the nanoparticle support interface can serve more than its typical role as an active site. In this other work, we show how the physical presence of the nanoparticle support interface directs secondary metal overgrowth and tunes the size of metallic ensembles on the nanoparticle surface. In this other work, we compare the palladium metal overgrowth step on supported gold nanoparticles or on unsupported gold nanoparticles before their immobilization under the support. I will not discuss this work in detail, but briefly, we adopted an integrated experiment, theory, simulation approach to derive design, structure, property relationships in bimetallic palladium gold supported catalyst design. We first characterized the palladium ensemble abundance and their size distribution on the nanoparticle surfaces, and correlated these structural features to their catalytic performance using theoretical calculations to elucidate the structure property relationships. Next, to understand how the initial catalyst design produces the types of palladium ensembles we observed, we performed numerical wetting calculations and molecular dynamic simulations accelerated by a machine-learned force field to understand palladium wetting on the gold nanoparticle surfaces and palladium migration during high-temperature calcination treatments to prepare the catalyst. We report that the synthetic sequence should not be chosen arbitrarily, as nanoscale wetting phenomena at the interface plays a non-innocent role in bimetallic palladium gold nanoparticle catalyst synthesis and their resulting catalytic performances. This brings me to the end of the second half of my talk. I have showcased how the partial nanoparticle embedding feature in the RCT method can be used strategically to alter both catalytic and synthetic outcomes. First, we illustrate how partial nanoparticle embedding can accentuate catalytic contributions arising from the interface. Here, partial nanoparticle embedding increased the nanoparticle support interfacial parameter, which created more gold titanium interfacial sites for benzaldehyde adsorption and reaction at the interface. Next, we briefly discussed how this nanoparticle support interface can alter the wetting behavior during the reductive overgrowth of a second metal on a nanoparticle host. This results in differences in the secondary metal ensemble size and leads to differences in their spatial distributions on the nanoparticle surface, which directly influences catalytic performance. Taken all together, my work is motivated by the limitations of existing catalyst preparative methods, where multiple structural parameters are coupled together during synthesis and change during reaction. Consequently, the strong coupling of structural parameters obscures the derivation of clear structure property relationships to guide our future catalyst design. I exemplify my motivation with two examples. In the first half of my talk, I explained why nanoparticle proximity and nanoparticle size are coupled together and cannot be independently varied from each other during synthesis. In the second half of my talk, I described how the support chemistry strongly influences the nanoparticle nucleation characteristics and thus precludes independent variation to isolate effects arising solely from nanoparticle support interactions. Moreover, under thermocatalytic conditions of high temperature, pressure, and mechanical agitation, these impregnated catalysts are prone to nanoparticle leaching and sintering, which further confounds our catalytic analysis. To address this challenge, I employed a modular raspberry colloid templating approach as a model catalyst platform to deconvolute the individual effects of these traditionally coupled structural descriptors. In this talk, I describe my contributions to the field of catalyst design through two works from my PhD. First, by using pre-synthesized colloidal nanoparticles and fully decoupling the nanoparticle and support formation steps from each other, I independently tune nanoparticle proximity and nanoparticle size to investigate their individual effects on catalytic performance. Second, the RCT method derives catalysts with nanoparticles partially embedded within the support, which not only improves catalytic stability against sintering, but also disentangles the support and embedding effects from each other to investigate the isolated roles of the nanoparticle support interface. These two works are just part of a larger body of my PhD, many of which I do not have time to discuss in this talk today. Importantly, the structural properties that I investigated, such as nanoparticle size, nanoparticle proximity, and the nanoparticle support interface, are found in practically all nanoparticle-supported catalysts, regardless of their preparation method. Therefore, I anticipate that the effects of these structural properties, which have been individually deconvoluted and unambiguously studied in my PhD, will be broadly translatable to existing catalyst preparative methods to design more active, selective, and stable catalysts in the future. Now we come to acknowledgements. And before I finish this talk, I want to take this time to acknowledge the many different people who have helped me along my PhD journey. The first is my advisor, Joanna Eisenberg. Joanna, thank you for your unyielding support to let me develop my research vision and for supporting my professional endeavors. Joanna has opened many doors and opportunities for me, both in research and in my endeavors, both inside and outside professionally. In research, I always am inspired by how you relentlessly pursue the ground truth and to always do purposeful work instead of just putting one paper out after another, where it's just incremental work. I think the most important thing that Joanna, you taught me was big picture thinking and storytelling. And so I hope today's story is a good reflection of your training and onto my development as a graduate researcher. So Joanna, I will strive to continue to approach my future research with the same amount of rigor and zeal and interdisciplinary way that you have taught me during the 4 years that I've been in your lab. The next two people are to my committee members, Adam and Jared. We meet once a year, but your continued support and your very timely responses have reduced my anxiety very, very much greatly. Although now I realize that you have one more chance later, but we'll see about that later. But I think very much the most important thing I took away from both of you is that if we have committee members outside my field, it would very much force me to reshape and think how I think about and communicate my science. And hopefully today is a good example of my development. I spent a lot of time in the Eisenberg lab, which was a very broad and interdisciplinary group. And all of your feedback have shaped the way I approach and do my work, even though most of you do not work in catalysis directly. I am most thankful for people who have helped me get started as a graduate student in the lab, and they include Jesse, Jay, Natalie, Jack, Anna, and to the rest of your group for your very good company over the past years. I want to take this time to highlight a few individuals who I have worked very closely in Joanna's lab. And the first is Michael Eisenberg. And thank you for your keen eye for detail. And that comes from someone who thinks I am very detailed, so I think I've met my match. And your feedback and are always in good faith. It always comes in good faith, and it has polished up the works that we have published and has always brought it up to the next level. The next person I want to thank is on Zoom. It's Selina. Dr. Selina Kaiser was a postdoc in Joanna's lab and adopted me as a student, as a trainee for the first 1 year and a half during my PhD. Selina, I just want to thank you for your kindness and mentorship, your generosity with time, and your patience to nurture this very impatient person. I was also very fortunate to work with two very wonderful students, that is Sadia and Marianne. Sadia for about 2 years as she was a research assistant in the lab, and Marianne for about 6 months as she performed her master's thesis research with me. Together, Sadia, Selina, Marianne, and I have accomplished a lot of work in a short span of time, some of which you have heard about in this talk today. And I'm very happy that Sadia and Marianne are both doing very well in their own PhDs. Apart from Joanna's lab, my second home at Harvard is the Friend Lab, which has now been slightly repurposed, but I've had many good memories over there in the first 2 years of my PhD. Cindy's course in surface science was the very first course I took at Harvard, and her course has left an indelible impact, unbeknownst to me at that time, on my research interests and my trajectory. And hopefully, together, Cindy also, at that point in time, also ran an Energy Frontier Research Center, which Joanna was part of, and it's called IMAS. And together, we have worked on many different projects, some of which you have seen today. And hopefully, you can see their influence together with Joanna's influence in the work today. The consortium is called IMAS, and this Energy Frontier Research Center allowed me to interact with and collaborate with many different IMAS groups, such as the groups of Boris Kozinski, Christian Ries, Anatoly Frankel, Philippe Sauté, and Matt Montemore. Together with these groups in the consortium and also groups outside the consortium, such as the groups from Jesse van der Hoven, Graham Hutchings, Ned Egan, and Todd Toops. All of these groups have shaped the way I think about catalyst design, synthesis, characterization, testing, and theory. I hope you can see all of your group's interests and influence on my work, and I hope that we can continue our collaborations and friendship in the future. I think a group of unsung heroes in my time as a PhD are that of the facility course. So I spent a lot of time at CNS. I think in my first year, I spent so much money at CNS that Joanna asked me to make a second account at CNS to split up the funding to 2 account streams. Good news is I've got more efficient at CNS now. But the strong support staff who I partnered with at CNS and also at the Northwestern Catalysis Facility have really brought up my work to a different level and with an amount of robustness that very few people and very few places can achieve. So I'm very thankful to the Harvard CNS, to the Geosciences Department, and also to Northwestern's Catalysis Facility for allowing me to spend some time partnering with you in your core facilities. The final group of people I want to thank are people back in Singapore, and they are my former PIs who took me on as an undergraduate researcher, to my family, friends, and to my partner, Rachel, who have stood resolutely with me since the very first day of my PhD, even though they are many, many thousands of miles away. Together with a larger group of friends, these people ground me every single day and remind me of my role more than just that of a researcher. So to all of you, friends, family, colleagues, collaborators, past, present, and future, thank you for believing in me and for your friendship over the many years and the many years to come. After my PhD, I will start as a Stanford Energy postdoc fellow in the fall, working with Matteo Cagnello and Tom Jaramillo on CO2 catalysis. And it's great because Joanna has heard me complain about the winter every single winter, and I very much look forward to escaping the winter altogether. Thereafter, I look forward to starting my independent research career in Singapore, and hopefully in a month or two, I will be able to share the official news with you soon. And with that, I think we are good on time. Thank you for listening, and I'll be happy to take your questions.
Now you can breathe, you can take a deep breath and come up with questions. Please do come up with questions and be from everybody else. But before that.
Yeah, of course.
You will. Okay, so questions from the room and then we will have a closed session.
Yeah.
Please. Yes.
Use gold palladium alloy. What do you think would change if you use, say, silver gold alloy? For example, what's the importance of the catalyst in that case?
Right. So the choice of the nanoparticle composition is flexible because you can synthesize the nanoparticles first, bimetallic, monometallic, or in different shapes, ways, and forms, and then you incorporate it into the catalyst. I think what's most important is to ask what kind of questions that I wanted to ask. And in the questions I wanted to ask, we wanted to have a very active component in the nanoparticles that is palladium, which would dissociate the small molecules like hydrogen and oxygen to perform hydrogenations and oxidations respectively. And you would have a very selective and stable host like gold nanoparticles, where they would stay stable under the reaction. But in principle, we have also explored silver gold alloys and other bimetallic compositions. And it's absolutely possible to prepare other types of sizes, shapes, nanoparticle compositions using the RTT method that I described in this talk.
Other questions? Yes, please.
Garrick, beautiful work, really amazing. I am not super familiar with the topic, but if I remember a bit correct, something about catalysis. If I remember, at some point you can have different type of behavior depending on the phase of nanoparticle that is exposed. So, did you actually consider that, or maybe you have also worked with that? You didn't talk in the presentation, but or have you thought how you can the type of experiment that you can actually do to achieve this or to control this?
Yeah, absolutely agree with you. So the question is whether the facets and the shapes, the faceting of the nanoparticles can be used as a tool to control and further fine-tune reaction performance, and that's absolutely possible. Many groups have done it, and it's absolutely possible, and in our way, we can do it too. I think it's more applied in terms of electrocatalysis and photocatalysis, where the reaction conditions are not so elevated in terms of temperature and pressure, because at temperatures at about 200 C and 300 C, and at high pressures, these surfaces are not as stable as we think we are, as you think we'd expect as you synthesize them, and they would restructure. So you see in the elemental mapping, they form quite like a round, amorphous, non-crystalline or polycrystalline nanoparticle out of it. So it'd be very difficult to deconvolute the effects out of it altogether. But it's entirely possible if you reduce the reaction temperature and use it for photocatalytic or electrocatalytic application, you will be able to use shape-controlled nanoparticles, and some colleagues in our groups have also done it. And if I can elaborate just a little further, the choice of the support does not need to be that of a solution phase precursor. So in this step, you can use preformed metal oxides, nanocrystals of perhaps titania, ceria, of well-defined facets, and you'll be able to jam them to form the entire support structure. And that gives you another lever to direct reaction performance, not just by using the nanoparticles to your advantage, which is what typically most people use, but also to use the support chemistry and nanoscale properties of the support, which is not quite possible with traditional methods, where you would form the support as a macroscopic scale on the micron scale. So I think that's what distinguishes our method from what is currently available and what's currently used industrially.
I can just follow up on
Yeah.
that. How would you be able to control which phase actually speaks out? Is there really precisely control, or you always are relied on statistics?
No, it's not quite statistics. It's quite statistical, but as with nanocrystal synthesis or the field of nanocrystal synthesis, it's always driven by thermodynamics and kinetics.
Oh, in your case,
But-
I mean. like in the Raspberry Pi.
Right.
How will you be able to? I know that if you have a nucleation, you can tune which phase, but in
Right.
this case, where you preload and then you do this, will you be able to do the same?
You probably would, because the choice of the nanoparticles and the way you synthesize it is pre-synthesized. So all we need to care about is the nanocrystal synthesis phase, and that the broad field where they study how thermodynamics, kinetics, for example, the choice of precursors, temperature, nucleation characteristics, will be able to tune this spherical particles to something more or to your liking, where you can choose to study shape or facet-dependent effects, and you will be able to load them. I think one thing, another comment I'd like to say is that the nanoparticles or nanocrystals, in your case, in your question, will be partially embedded, and that stabilizes the nanoparticles even more, although one has to be very cognizant of the problem, or rather of the effect that the support, because it has so much of an interface and contact with the nanocrystals, it might change what will be the thermodynamic phase of these nanocrystals that fall.
Thank you.
Michael?
Wonderful work, Garrick, and wonderful presentation. Care to say a few words about what you're gonna do with CO2? Gas phase, solution phase, supercritical phase, reaction phase?
Yeah. So my plan at Stanford is to work on thermocatalytic CO2 hydrogenation to fuels, C2 fuels. So I like to control the microenvironment around the active site, where you'll be able to balance the carbon-oxygen activation together with the carbon-carbon coupling. So it's very much like a polymeric chain kind of problem, where you try to break and try to form C2 molecules from C1 molecules. So for example, you try to form ethanol. And my argument is that if I can form the first carbon-carbon bond, the second, third, and the subsequent bonds would be more easy to form compared to the first one. And that's the fundamental insights that I'm going for. And it will be in the gas phase, right? Because the CO2 comes at a high temperature and high pressure. And then you would form the alcohol products, but at that reaction temperature and pressure, it will come out as a gas. And then you will condense it, and you will collect it and do your analysis out of it.
Any benefits from potential supercritical?
Sorry?
Any potential benefits from supercritical phase? No?
Yeah, I've seen some people use supercritical CO2. I think the broader motivation of trying to use CO2 to convert them to fuels, as with some other people have done that, is to be able to use CO2 from either flue gas or carbon capture sources, wherever they will capture the source, and then we will be able to use that amount of dilute CO2 to form the fuels that we use. So I'm trying to come from the direction where we use CO2 captured from point sources where the CO2 levels are a little more elevated, not quite supercritical CO2, because if you think about the techno-economics of it, you would have to bring it to supercritical CO2, and then I have to give extra energy to form the fuels, and at that point in time, it might just be easier to form the fuels using Fischer-Tropsch synthesis or some other forms of methods.
Thank you.
Yeah.
I saw another
Anna.
hand here. Sometime, it was Anna.
I had a question, maybe this was what you were considering at the outset before you went into very fundamental, which is, can you comment on, like, if you have different nanoparticles of different composition near each other? For example, like how in biology on a membrane you have enzymes in proximity with one another to conduct some catalytic reaction. I
think that's the most interesting part of it, your question, Anna, and that's something I started in my very first group meeting when I presented to Joanna and to the group meeting, is that many catalytic reactions and many catalytic cascades in nature rely on more than one type of active site. In this work, mostly I've relied on one type of nanoparticle and one type of active site to drive a very simple reaction so that we can study the effects of different structural properties. But for example, in my proposed postdoc work, where you like to convert CO2 to multi-carbon products, you would have a process where you might convert CO2 to methanol, or CO2 to carbon monoxide, and then you would have to increase the chain length. And in that case, you would need to have different active sites. It might be loaded on the same nanoparticle, but most probably you would load it in different nanoparticles, And using this method, you could have one pore decorated with one type of nanoparticle and another pore decorated with another type of nanoparticle, so that the reaction cascade can go in with the prescribed reaction flow and the mass transport flow direction that you want it to go.
Would you want them on different pores or even in the same pore having multiple, because you can load your colloidal particle with multiple different nanoparticles, right?
And I think that's the most interesting thing about it, right? Because in reaction engineering, in the field of reaction engineering, people have studied catalyst bits of one catalyst, catalyst bits of two catalysts, where they're either mixed together as granules or mixed together as a bit. So there is a macro scale mixing, there is a micron scale mixing, but they never quite achieve a nanoscale mixing, which is what this platform can achieve. And I think this is what complements what reaction engineering practitioners are currently using to be able to bring the reaction and its investigation of structural properties from the macroscopic scale all the way back down to the nanoscopic scale.
Any other questions? With that, let's thank you. To step away, don't go far. And the
committee will meet, the Zoom session will end, and then later we'll reconvene for champagne and hopefully a pass. Hopefully. But to everyone on Zoom, thank you for coming, and I'm going to end the recording on Zoom, but thank you so much for coming.
Ciao. Thank you.
Thank you.